You're adrift in your vision. A silent, velvet black sphere just keeps growing. The stars around it start to warp, twisting into a light show that's as beautiful as it is terrifying. You've just passed the point of no return. What happens now? This isn't just a story about some distant, nameless astronaut. This is your time's journey. For the next few minutes, this is your reality. You are falling toward the most extreme and baffling object in the known universe. A place where gravity is so powerful it warps reality itself, and where the laws of physics, as we know them, just give up. But what happens? To you, your fate depends entirely on one thing: the size of the black hole you're falling into, because not all black holes are created equal. The difference between a small stellar mass black hole and a supermassive giant is a difference between a swift, violent end before you even get started and a slow, mind-bending fall into the heart of space-time itself. So let's take the scenic route. Let's imagine you're falling toward a supermassive black hole, millions or even billions of times the mass of our sun, like Sagittarius A, times at the center of our own Milky Way galaxy. Your journey starts now. Section 1. The approach. A deceptive calm from far away. A black hole is surprisingly ordinary. Its gravity is no different than a star or planet of the same mass. If you swapped our sun with a black hole of the exact same mass, the Earth wouldn't get sucked in. We'd keep orbiting just like we do today. That popular image of black holes as cosmic vacuum cleaners is mostly a myth. They're more like passive giants. But you're not in a stable orbit. You're falling. As you get closer, the first thing you notice isn't a feeling, but a sight. The black hole itself is the most perfect darkness imaginable, an absolute void of light. It's a pure shadow cast on the fabric of the cosmos. The space times around times it, though, is a whole different story. It becomes a carnival of distorted light. This is called gravitational lensing. The black hole's immense gravity acts like a lens, bending starlight from galaxies far behind it. You'd see strange, warped arcs and even multiple images of the same star as its light takes different paths to reach your eyes. The universe starts to look like you're seeing it through the bottom of a wine glass. And right around that sphere of darkness, you might see a bright, thin ring of light. That's the photon sphere, a region where gravity is so strong that particles of light, photons, are trapped in orbit. Some of this light has circled the black hole multiple times before escaping to reach you, showing you images from the distant past as you keep falling. Another weird visual effect kicks in. The stars ahead of you seem to shrink into a small, bright blue window. That's because you're accelerating to incredible speeds, compressing the light waves in front of you and shifting them to bluer frequencies. If you dare to look back, the universe you left behind would seem to spread out, growing redder and dimmer. And through all of this, you feel nothing. You're in a perfect state of freefall. Just like an astronaut orbiting Earth feels weightless. You feel no pull, no force, nothing to signal the incredible danger you're in. Your body feels completely normal now. If you were falling into a small stellar mass black hole, this wouldn't be the case. The difference in gravitational pull between your head and your feet would be enormous, even from far away. These tidal forces would stretch you apart in a process we'll get to in horrifying detail soon. But you chose the supermassive giant. Its incredible size means space-time curves more gently at its edge. The tidal forces are so weak you don't feel a thing. And so you continue to fall, weightless and unharmed, towards the boundary of no return, the event horizon. Section 2. Crossing the event horizon. Two versions of reality. The event horizon might be one of the most misunderstood concepts in physics. It isn't a physical surface you could touch. It's a mathematical line in the sand. It's the exact point where the gravitational pull becomes so strong that to escape, you'd have to go faster than the speed of light. And since nothing can, all paths beyond this point lead inward. For you, the moment of crossing is completely uneventful. You'd sail right past this invisible line without feeling a thing. No alarms, no bumps, no sudden jolt. From your perspective, you're still in a peaceful freefall. You might not even realize you've crossed the point of no return. But for someone watching you from a safe distance, say, a friend with a ridiculously powerful telescope, the story is totally different. From their perspective, as you approach the event horizon, time for you appears to slow down. This is a real consequence of Einstein's theory of general relativity, called gravitational time dilation. Your movements would get slower and slower. Any light signals you send back would get redder and dimmer. As you get impossibly close to the horizon, your friend will see your image seem to freeze, stretched across the boundary, slowly fading over an infinite amount of time. From the outside universe's perspective, you never ever cross the event horizon. You become a frozen ghost on the edge of the abyss. Your reality, however, is the complete opposite. Now that you're inside, if you turn to look back at the universe, you'd see something spectacular. Because time for you is now running slower than for everyone else, the future of the cosmos would play out in fast forward. You might see stars age and die in seconds, and galaxies evolve and merge. You are watching the future of the universe unfold, but you can never go back. You're completely disconnected from its space-time. In here, the roles of space and time have swapped. The direction toward the center, the singularity, is no longer a direction in space, it is the future. It's as unavoidable as tomorrow. Section 3, Spaghettification, the ultimate stretch. That peaceful, weightless fall doesn't last. You survived crossing the event horizon, but your doom was only postponed, not cancelled. As you get closer to the center, those gentle tidal forces start to grow exponentially. Now, you're about to experience a process with a terrifyingly accurate name, spaghettification. Popularized by Stephen Hawking, this is what happens when you enter an extremely non-uniform gravitational field. As you fall feet first, the gravitational pull on your feet becomes astronomically stronger than the pull on your head. That tiny difference is now a colossal differential pull that stretches you. At first, it's just a slight tug, but it intensifies with shocking speed. The pull on your feet becomes billions of times stronger than on your head. Your body begins to stretch vertically like taffy. At the same time, because all matter is being pulled toward a single point, your sides are squeezed inward. You are being simultaneously stretched and compressed. The experience would be agonizing. Your bones would snap. Your muscles and tissues would be torn apart, followed by the molecules and then the atoms that make you times you asterisk. You'd be rendered into a long, thin stream of subatomic particles, a river of matter flowing toward the center. You're being literally deconstructed by the raw curvature of space-time. This whole horrifying process would happen in less than a second once the forces become unbearable. Remember, if you'd have picked that smaller black hole, this would have happened times before times you even reached the event horizon. The only mercy of a supermassive black hole is that you get to see inside before being torn apart. If you're finding this journey into the cosmos as mind-bending as we are, consider subscribing. We dive into the universe's biggest questions every week, and you won't want to miss where we're going next. Now, back to our final destination. Section 4. The singularity, the end of physics. That stream of particles that was once you has only one place left to go, the very center of the black hole, the singularity. What is a singularity? In Einstein's theory of general relativity, is the end of the line. It is a point of zero volume and infinite density. It's a place where the mass of millions of stars has been crushed into an impossibly small space. Here, the curvature of space-time, what we feel as gravity becomes infinite. The very fabric of space and time is torn apart. At the singularity, all the known laws of physics break down. General relativity, our best theory of gravity, starts spitting out infinities, which is a scientist's way of saying the theory has stopped making sense. It's like trying to divide by zero. The answer is undefined. We just don't have the tools to describe what happens here. To really understand it, we'd need a theory of quantum gravity, one that unites the physics of the very large, like gravity, with the physics of the very small, quantum mechanics. We're not there yet. The singularity is the frontier of our knowledge, where our two best descriptions of the universe fail spectacularly. So, what's your final moment like? What happens when the stream of your atoms hits this point of infinite density? We can only guess. Perhaps you're simply crushed out of existence. Some theories speculate about a firewall of energy that would incinerate you. Others, more exotic, wonder if a singularity could be a gateway to another universe. But based on our most trusted theory, the singularity is simply the end. An end not just for you, but for time and space itself. It's the ultimate unknown, a place from which no information can ever escape to tell the tale. Your journey is over. It began with a silent, peaceful fall toward a sphere of perfect black. You watched the universe warp and bend. You crossed the invisible point of no return. A profound moment that you didn't even feel. From inside, you watched the future of the cosmos flash before your eyes. Then came the inevitable violent end. You were stretched and squeezed by colossal gravity, torn apart atom by atom. Your remains completed the final journey, plunging into the central singularity, a point where our understanding of reality itself collapses. Falling into a black hole is a journey that separates you from the universe, first by the illusion of time, and then by the absolute barrier of the event horizon. It's a story with two different endings: the frozen, fading image seen from the outside, and the brief, spectacular, and ultimately horrifying experience of the one who falls in. And it teaches us that the cosmos is not only stranger than we imagine, it's stranger than we times can times imagine. Thank you for joining us on this fall into the abyss. Until next time, keep looking up.